Hello and welcome. This is Cambridge O-Level Physics paper number 2. The subject code is 5054. This is May-June 2022 exam and this is variant 2 of this paper. Let's start. Section A. It says answer all the questions in this section. Answer in the spaces provided. Okay. So first question, it says figure 1.1 shows a water skier pulled horizontally across the water surface. The mass of the water skier is 60 kgs. The gravitational force strength G is 10 Newton per kg. The first part A, it says calculate the weight of the water skier. So now we have to calculate the weight. So we know that weight W is equal to mass times the gravitational field strength. So mass is 60 kgs multiplied by 10 newtons per kg. So kg cancels. This comes out to be 600 Newton. So the weight is 600 Newton. Okay. Next part B. It says mass and weight have different units. State two differences between mass and weight. So remember, so mass is a scalar quantity, whereas weight is a vector quantity. So this is one difference. Then we can say that mass varies with proportion. Oh, sorry, mass does not varies with proportion. Uh, it does not varies with proportion. It is an inherent uh, value of any material or any substance, whereas weight varies with proportion and the gravitational field strength. Gravitational field strength. Okay, so this is another thing. So these are, you can say, the two differences between mass and weight, and you can always go with it. So remember, one is, if you remember this formula, so mass multiplies times the gravitational force strength is the weight. So mass is an inherent quantity or value of any substance, and the weight is actually the effect of gravitational strength on field strength on it, and that basically makes it as a vector quantity. So mass is a scalar quantity, weight is a vector quantity, and then mass does not changes with doesn't varies with proportion, whereas weight varies with proportion, and with the change in gravitational field, the overall weight of that thing will change. So moving ahead, part C, it says a boat pulls a water skier to right with a horizontal force of 50 Newton. The water skier travels at constant speed. So part 1 is explain in terms of horizontal forces acting why the speed is constant. So if you are going to see this photo, it will say that the 50 Newton is acting in this direction, and the weight of the water skier 600 Newton is acting in this direction. And say the water friction, you can say it is F, force friction is acting in this direction. Okay, so this is the overall situation over here. So now this water sphere is moving with a constant speed. So explain in terms of horizontal forces acting, why the speed is constant. So we saw that the horizontal force, that this is the forward acting force, I call it as F forward, was equal to 50 newtons. And the force of friction that is acting uh, is, I mean, we don't know it, but since it is moving with a constant speed, it means that the forward force is balanced by the force of friction. And that is why the uh, the person or the water skier is moving with a constant speed. So we have to basically explain all of this in terms of these forces acting on the speed. So we can just simply write that the horizontal forces cancels out each other. So this 50 Newton force is cancelled out by the force of friction, and overall there is no resultant force. So no resultant force. So F resultant is equal to 0. And that means that it is moving with, there is no acceleration or constant speed. So let's write it. So we can say that uh, the pulling force of 50 newtons is balanced by the uh, friction force because of air plus water. The water friction or the air friction is balanced by the air, is the resultant force acting on the water sphere is 0, thus moving with constant speed. Okay, so this is how you can explain the situation over here. So moving ahead, uh, question C, part 2, it says a horizontal force acting to the right increases from 50 Newton to 70 Newton. The sizes of any other forces are unchanged. So calculate the acceleration of the water sphere. So this one was, for example, our person, and we were saying that 600 Newton was acting this manner. So 50 Newton was acting this, and the force of friction was 50 Newtons in this. So now this has changed to, added 20 Newtons here. It has changed now to 70 Newtons. So what will be the acceleration? So we remember that force of acceleration is uh, mass times, sorry, a force is given as mass times acceleration. So we know that the change in force or the effective resultant force that is acting on the rider is now Fr is equal to 20 newtons. 20 newton has increased in this direction, so the effective force is 20 newtons. And the mass of the rider is 60 kgs, and we have to calculate the acceleration. So acceleration will be simply 20 divided by 60, and this comes out to be 1 by 3 meters per second square. Or you can always say as acceleration 1 by 3 meters per second square, or 0.333 meters per second square. Any of these values will give you the right answer to this question. Okay, so moving ahead, question number 2, it says figure 2.1 shows a long cardboard tube sealed at both ends, which contains many small pieces of metal. So here we see this tube. These are small pieces of metal, and these two ends are sealed. So it says the tube is turned vertically, so the pieces of metal fall from one end to the other. The temperature of the pieces increases as a result of the fall. During the fall, the gravitational potential energy of the metal pieces is transferred to other forms of energy. State two other forms of energy to which the gravitational potential energy is transferred. So what we are doing, we are basically turning this tube from horizontal position to vertical position. And during this case, what happens is that the potential energy changes. So these pieces of metal fall from one end to the other end, and that will change the potential energy or the gravitational potential energy of these metal pieces into kinetic energy. Some sound will be produced, and the temperature of the pieces is also rising. So we know now three forms of energy. So one is two forms of energy. So one is heat energy, the temperature. The question is already talking about. Number two, there will be some sound that will be produced, sound energy, you can always say. And number three, the particles will fall under the effect of gravity, and that changes the gravitation potential energy to the kinetic energy of the metal pieces. So kinetic energy of the metal pieces. Okay, so these are our three forms of energy. Any two forms you will be mentioning will be fine for your complete credit. Then part B, it says the pieces fall an average distance of 1.2 meters during one turn. The total mass of the metal is 150 grams. It says calculate loss of gravitational potential energy of the pieces as they fall once. So for example, so the distance travel, distance, this is D, is 1.2 meters, and mass over here is 150 grams. So remember, potential energy over here, and say if they are on rest over here, there is no potential energy. So potential energy is given as mass times gravity into height. So mass is 150. Now remember, this is in grams, so we have to change it into kilograms. The units are very important here. Multiply by strength of gravity 10 newtons per kg, multiply by height, that is 1.2 meters. So now this will give you the value of the potential energy, and that energy will be equal to 1.8 joules. Okay, so the answer will be 1.8 joules. Then part 2, it says the student turns the tube quickly after small pieces of metal have fallen from one end to the other 80 times. Okay, and the temperature has increased by 7 degrees centigrade. So determine the specific heat capacity of the metal. Specific heat capacity, so remember that specific heat capacity Q is given as mass mc delta theta, and C is your specific heat capacity, or small c. We have to find out, so first of all, we have to find the total energy, QT. So loss in potential energy was 1.8 in one fall, and the student has done it 80 times, so multiply it by 80, and this will give you the total energy that will be equal to 144 joules. And the change in temperature from the question, we found out that it is 7 degrees centigrade, and we all have the mass that is equal to 150 grams divided by 1000. This is equal to 0.15 kg. The specific heat capacity, the value of C will be given as Q over M delta theta, and this is equal to 144 divided by 0.15 multiplied by 7. So the answer comes out, the value of C 137.142 joules per kg per degree centigrade. So this is your value. So um, with this, you can simply write 137.142 joules per kg per degree centigrade. So this is the value of your specific heat capacity for this question. So next question, part B, and the third part of this question. It says the student repeats the experiment, turning the tube more slowly. It says suggest why a different temperature increase is obtained. So now if you're going, or in such an experiment, if you're going to rotate or turn the tube uh, slowly, what will happen is that the average kinetic energy of the pieces will decrease. So the average kinetic energy of the pieces, when decreased, there will be less friction losses uh, against the, or there will be less velocity of the metal pieces striking each other, and the striking of each other results in friction that increases the temperature. So if the velocity is low, the overall change in energy will be low. So this will results in much less temperature change compared to the earlier cases. So, or you can say that the friction loss will be much will be lower, and that will um, result in change in or a different amount of temperature increase as compared to the earlier case. So let's try to write this. So lower velocity results in lesser kinetic energy of the metal pieces. This results in less friction loss, which results in change in temperature of the tube. And so this is how you can simply write this thing. So less velocity means less kinetic energy. Less kinetic energy means less friction. Less friction results in less change in temperature across the tube. Okay, so these 4 points you have to mention. So now moving ahead, question number 3. It says figure 3.1 shows a syringe mounted vertically in a block of wood and sealed at one end. A plunger is free to move inside the syringe. There is air, there is trapped air inside the syringe. The air inside the syringe exerts pressure on the walls of the syringe. So part A, question number 3, part A, it says define the term pressure. So remember, pressure in our formula, pressure is equals to force acting per unit area, or sorry, A. So we just simply write pressure is defined as force acting per unit area. Okay. Then part B, it says explain how the air molecules in the cylinder of the syringe create a pressure. So the air molecules, remember, the air molecule trapped inside the string, they are moving at random, and they possess some kinetic energy. And once they're moving at random, they strike across the walls of the syringe, And when striking across the walls of the string, they exert a certain force across those walls, and those forces acting per unit area, and that eventually turns it into a pressure as pressure acting on the string. So let's write it out. So you can say that air molecules are moving at random. Molecules are moving at random and possess kinetic energy. Kinetic energy. They strike the walls of the syringe cylinder, resulting in force acting per unit area of the cylinder. This results in pressure acting across the walls or of the syringe cylinder. Okay, so moving ahead, question number 3, part C, it says a 10 Newton weight is placed on top of the plunger. The plunger moves down so that the temperature of the air inside the syringe does not change. Before the weight is placed on top of the plunger, number one, the pressure of the air inside is 1 into 10 power 5 pascals. Number two, the volume of the air is 50 centimeter cubes. We call it P1 as say 10 to power 5 pascals. V1 is equal to 50 centimeter cube. The cross-sectional area of the plunger is, so area is 1.2 into 10 to power minus 4 meters square. So it says calculate the pressure of the air in the syringe after the plunger stops moving. Okay, so after the plunger stops moving, uh, we have to find out the pressure. So pressure, remember, equals to force acting per unit area. So the force after the so we have 10 Newton placed on top of the plunger. So the force acting, uh, or you can say the resultant, yes, pressure. So pressure because of this 10 Newton weight will be say 10 divided by what the area is 1.2 into 10 to power minus 4. So this comes out to be 8.333 into 10 to power minus 4 Newton per meter. So this is pressure because of this 10 Newton weight. So the overall pressure, the total pressure of air after the plunger stops moving will be the initial pressure, P initial plus pressure because of this 10 Newton weight. The initial pressure was 10 power 5 pascals plus this is also equal to 8.33 into 10 to power 4. It's not minus 4, 10 to power 4 pascals plus 8.333 into 10 to power 4. So this comes out to be 1.8333 to 10 to power 5 pascals. So the answer will be 1.833 into 10 to power 5 pascals. Okay. Or you can also write 1.833. Other units are Newton per meter square. that is also equal to pascals. Pascals, you can also write this, or Newton per meter square, or yes, instead of this. So it's up to you. Okay, anyway, do not forget to write units. They are very important. You will lose some credit if you're going to miss out on these. So moving ahead, question number two, it's sorry, part C, question number part C is part two. It says calculate the volume inside the syringe after the plunger stops moving. So remember the law, and it says the temperature. So initially we know that P1 V1 over T1 equals to P2 V2 over T2. This is the law which we have studied in our course. So since temperature is not changing, we are not considering our temperature. So what we are left with, P1 V1 equals to P2 V2. So we have to calculate the volume inside the syringe after the plunger stops moving. So we have to calculate V2. So we are given with initial pressure 10 to power 5 pascals. Initial volume was 50 centimeter cube. Pressure to after the plunger has stopped moving, let's call it. So these are, say, our initial values, and these are our final values. So final pressure was 1.833 10 to power 5, and my final volume is V2. So we are going to calculate V2 from here. V2 will be equivalent to 27.272 centimeter cube. Okay, so our volume will be 27.272 centimeter cube. Okay, so this is how you will solve this question. So moving ahead, next question, question number 4. Question number 4, it says figure 4.1 shows a ray of white light incident on a glass prism. So we have a prism over here. The white light is coming. The white light is breaking down into its component color because of the prism or the different refractive index. And then it's coming out of the prism, and then there is bending of light as well. So the refraction causes white light to separate into different colors. So this is what exactly is happening here. So it says define the term angle of reflection. So remember, the angle of reflection is the angle between the reflected ray and the normal ray. So for example, if this is, and you make a normal over here, angle of refraction. So this is my incident angle. And if I'm going to go like this is the refractive angle. So this is theta. So I call this as theta r, or refractive. The angle between the normal and the refracted ray. Okay. So just simply, it is the angle between the normal ray and the refracted ray in a medium. So this angle, or actually it generally it is a acute angle, but we can just simply say that it's the angle between the normal ray and the refracted ray inside a medium. Okay, so moving ahead, part B, it says angle of incidence, or you can call it as theta I, of white light as it enters the prism is 40 degrees, and the angle of refraction for the red light, or you can call it theta R, is equal to 25 degrees. Calculate the refractive index for the glass for red light. So remember, we have to use Snell's law here. So Snell's law, it says that a refractive index of air, sine of theta I, refractive index of glass sine of theta r. Okay, so simply refractive index, the light is going from air to glass, air to glass, sine theta I over sine theta r. Okay, so it comes out to be, or you can call it, or generally in easy ways to see n a is equal to 1, or the refractive index of air is taken as 1. So if you're going to take it as 1, you have to find out this, or the refractive index of glass. That will make this thing more easier for you to understand. So Ng. So remember, the ray is traveling from air to glass. So sine theta I, so we are sine theta of 40 degrees divided by sine theta of 25 degrees. And this comes out to be equal to 1.5209. We can call it as approximately 1.521. So refractive index is 1.521 in this case. So remember, if our light was traveling on the other direction, this formula would have been reversed. So from, if it had been traveling from the glass to air, uh, things would have been a little bit different. But again, in that case, the refractive index of glass will not change, but our scenario will have to, or I mean, in the calculations, you always have to make sure that the medium from which the light is traveling, or one medium to the other when it's traveling, you have to especially take care of that. But anyways, moving ahead, question part C, it says figure 4.1. Using the figure 4.1, state and explain how the refractive index of red light differs from the refractive index for the violet light. So remember, uh, the refractive, so the red light, it is violet light is bending more compared to the red light. So the refractive indexes will, for both of these lights, will be different. So we can simply say that the refractive index is smaller for red light compared to refractive index for the violet light, because violet light is more bent, is having more refraction compared to the red light. So we using the figure, so we have to explain, at least give, there's 2 marks, we have to give these 2 points. So number 1, the refractive index is smaller for red light sorry. So refractive index is smaller for red light, and so the refractive index is smaller for red light compared to, okay, to violet light. The larger refractive index results in more bending of light. And we have seen from the figure that it shows that the violet uh, light is having more bending compared to the red light, and that is why what we can say from here. So moving ahead, um, again, it's the same part. We're using explain the refractive index of light differs from the refractive index of the violet light. So we have explained this in this part as well. So part number D says the source of white light used in 4.1 produces other types of electromagnetic radiation as well as white light, visible white. State what is State the name of invisible radiation found at P uh, and the invisible radiation found at Q. So remember, the visible light produces um, or it's an electromagnetic radiation, VIBGYOR. So this is the red light and this is the violet. Red bends the least, it bends the most. So on the spectrum, on the visible spectrum, say if we have red here and violet here, so the whole visible spectrum lies inside it. So above here we have infrared and below here we have ultraviolet. Okay, so let's see what is there in our picture. So above red we have infrared and below Q we have ultraviolet. Okay, so Q will be ultraviolet, red will be the infra or P would be infrared. So that is the best way to remember red. The next electromagnetic radiation towards the red side will be infrared, and on the Q side, if it's violet, that would be ultraviolet. Okay, so P will be red or infrared will be infrared and Q will be ultraviolet. Oh, violet. Okay, so this will how we are going to solve this question. So moving ahead, question number 5, it says part A, a student connects a battery, a thermistor X and a resistor Y in parallel. The electromotive force or EMF, or you can say the voltage of the battery is E. The current X is I. The current through uh, this thermistor, this is, remember, this is your thermistor and this is Y is your resistor. Okay, so the current to the thermistor is I and the resistance of, and it says the resistance of Y is greater than the resistance of, so RY is more than resistance of Rx. Okay, so now we have to say take two boxes, one to show the correct statements above the potential difference across Y and about the other to show the correct statement about the current in Y. Okay, so remember we have a circuit like this. I'll draw it again. This is your voltage source and this is your thermistor and this is your resistor. Okay, so now we have these two are both connected in parallel. So whatever the voltage that is appearing across the thermistor X will be the same that will be occurring of Y. So the both voltages will be equal. So the potential difference across Y will be equal to E. And the same value E, that is the value of E, voltage across X will be E and the voltage across Y will be E, or the potential difference. Then you have current I that is flowing through this resistance, and this is the value is Rx, and you can say it's Ry. So what we can say about the value of current in Y? So remember, uh, larger the resistance, less will be the value of current. So whatever is flowing in I, the value of current in Y will be less than value of current that will be flowing in R. So remember, because current is equal to E divided by R, or Ohm's law, equals to IR EMF, or EMF you can also call it as V. So I can write it is much easier, V by R, or V equals to IR. Okay. So if my voltage is same across X and R, so Ix is equal to V divided by Rx. Okay, so this is the value of, so if my voltage is same, and my resistance value is more, then my value of current will be lesser. So I will be less than equal to, sorry, less than value of I will be the right choice for this case. Next part B, it says the student connects the thermistor X in series with the resistor Y, and the EMF and a battery of EMF of 6 volt as shown in figure 5.2. It says the circuit is at a room temperature. The resistance of thermistor X is, this is 600 ohms, and the current in the thermistor X is, the current flowing through this thermistor is 0.002 ampere, or you can call it as 2 milliamps. So it says calculate the power produced by the thermistor. So remember, power is equal to I square R. Okay, so the current, that is 2 milliamperes multiplied by 2 and by 600 ohms. So overall, it comes out to be 2.4 milliwatts, or the power will be 2.4 milliwatts. So remember, there are three other formulas: P equals to VI, then V square over R, and power is also equal to, sorry, I square by R. So these are the three formulas which you can use to calculate power produced in any passive any component, whether a resistor, thermistor, or a light dependent resistor LDR. So you can always use depending on what are the values you are given with. So we are given with the current through the thermistor, and we are given with the resistor. So easiest way is to use these two values. Okay, moving ahead, it says calculate the resistance of Y. Okay, so remember, you are given the value of current in the circuit. If you're going to see, uh, so this is my circuit. So this is your thermistor, uh, and this is your resistance. So this is thermistor X, this is resistance Y, this is 6 volts. And the current, remember, it is in series, it is given as 2 milliamperes. So you are given with the value of current, that is 2 milliamperes, and that is flowing through both these values, X and Y. So overall, we know that the current in the circuit, that is, sorry, 2 milliamperes. Overall voltage uh, that is applied across the circuit, voltage applied across the circuit is 6 volt. So the overall resistance, total resistance is will be equal to V by I. And I'm doing this with the help of Ohm's law. V equals to IR. So R is equal to V by I. And that is why I have written this formula. So the total resistance will be 6 divided by 2 milli. And that will be equal to 3000 ohms. And that will be the total series resistance of the circuit. So this total series resistance will be equal to resistance of the thermistor X plus resistance of the resistor Y. So I have the total value that is equal to 3000. The value of thermistor or the resistance is 600, plus I have to find out the resistance Y, and the resistance Y is equal to 2400 ohms. Okay, or you can also write it as 2.4 kilo ohms. So the resistance comes out to be 2400 ohms. So do not forget to mention the sign, or you can write it as 2.4 kilo. Okay, so now part 3, it says thermistor. The thermistor is cooled. Explain why this causes the potential difference across Y to decrease. So remember, the resistance of thermistor is directly proportional to temperature, or sorry, it is inversely proportional to the temperature. So if the temperature is decreased, the resistance of the thermistor will increase. So it says if the thermistor is cooled, so the potential difference across Y2 is decreased. So let's first I'll try to explain it with the help of circuit. So if your resistance is increased, there will be more potential drop across the thermistor and less potential drop across the resistor Y, or whatever the initial potential drop across this resistance X, it will increase, and that will result in decrease in potential drop across Y, because the overall voltage that is appearing between, you can say, A and B is 6 volt. And if this resistance increases, there will be or the value of resistance increases, overall potential drop across this will overall increase. The current will increase, overall the current through the circuit will uh, decrease, but overall this uh, drop across this thermistor X will increase. So overall, or let's try to write this answer. So the cooling of thermistor increases the increasing its resistance. This increases the total resistance of the circuit. So the resistance increases. This results in decrease in current across the circuit, which results in decrease in potential difference or voltage drop, or you can say voltage drop across the resistance Y. Okay, so in terms of explaining it, let's say our initial value, or initially we are following this. So the new resistance, let's call this R1 and I1. So V is constant. So what happened now that R2 is now greater than R1, this will result in decrease in value of I2. I2 will be less than I1, and that product will remain the same. V, or the voltage will remain the same. So the voltage drop across Y, voltage drop across Y will be I2 times RY. And since this I2 is less than I1, so the voltage drop will be less than what it was earlier. Okay, so moving ahead, question number 6. Question number 6, it says A figure shows part of a toy which contains two ring-shaped permanent magnets. A plastic rod passes through the center of both magnets. So the top magnet can move up and down freely through the around the plastic rod. The magnet poles on the bottom of the magnet are shown. So number one, so the top magnet floats in the air above the magnet. Okay. On the figure 6.1, mark the poles on the top magnet and explain why it floats in the air above the top magnet. So since there are two magnets, and if it's floating, it means that there are some similar poles which are repelling it. So this is north, so north repels north, it's north, and the south is here. So it would be something like this, because if there will be south pole on the bottom side, it would have been the bottom magnet would have attracted the top magnet and what won't be floating above. Okay, so let's explain it. So the north pole on the top magnet is facing the north pole on the bottom magnet. North pole of the top magnet faces the north pole of the bottom magnet. Similar poles repel each other. And this results in a force of repulsion with each other, and um, the force of repulsion is greater than the weight of the top magnet. Okay, so this will result in this magnet floating. But so if the force of repulsion would be lesser than the weight of that magnet, won't be floating above the top magnet. Okay. So part two, it says top magnet is replaced with a ring made of iron. Explain why the iron ring sticks to the bottom magnet. So iron is again magnetic material, uh, and when it's placed in proximity to a magnetic field, the magnetic field induces opposite poles, and it induces opposite poles, and which results in attraction of the magnet towards that magnet. Um, so let's write it. So iron is a magnetic material. Uh, Magnetic field from the bottom magnet induces south pole at the adjacent or lower end of the iron ring. The opposite poles attract each other. Thus, the iron ring is pulled to the bottom magnet and it sticks to it. Okay, so this is how you can easily write the answer to this part. Moving ahead, it says a wire carrying a current passes at right angle through a piece of paper. Figure 6.2 shows a cross section, a cross and a circle where the current in the wire passes into the plane of the paper. It says on this figure 6.2, sketch 3 magnetic lines to show the magnetic field pattern around the wire. Show the direction of your sketch of the field. So remember, a cross means this cross means into the page, and if there is a dot, it means out of the page. And for such a case, a current carrying conductor results in a magnetic field around it. So if a current carrying conductor, you have to use your right hand rule, and the thumb will be pointing towards the direction of the current, and the curled fingers of your right hand will be the direction of the magnetic field. So if I use my right hand, my thumb will pointing into the page of paper and my curled fingers will be pointing in this direction. So it would be something like this. And I have to show 3 lines. So I have to show 3 equidistant lines and 3 circular and equidistant lines. So I would ask you to pardon my drawing here, but make sure you draw them as equidistant or equispaced as possible. So something like this will be, or you can say call it as concentric circles. Okay, so make 3 concentric circles equally spaced. Okay, and so the 2 points will be one for the concentric equally spaced circles and the other will be for the directions. Okay, so make sure you do not you draw it correctly. Okay, so that's question number 6, and this concludes our section A for this paper. So now moving ahead, in section B, it says we have to answer 2 questions from this section, but I'm not that lucky enough, so I will be answering all the questions for you. So let's start with it. So question number 7, it says the figure shows a speed time graph of a car traveling on a straight horizontal road. So describe the motion of the car. So if I see from here, the car is accelerating uh, for the first 10 seconds, then it moves with constant speed and then decelerates in the last 4 seconds. Okay, so so let's so what's the acceleration here? So the acceleration, if I'm going to try and find out, it will be 16 divided by 10, or the slope of this line. The slope of this line is you can say 1.6 meters per second square, and the acceleration or the deceleration here will be last 4 seconds, or again the slope of this line uh, is 16 divided by 4, and it's 4 meters per second square, or deceleration. Since acceleration is a vector quantity, so you can also write it as -4, but let's have it in this way. So let's describe the motion. So first thing, the car accelerates for first 10 seconds at 1.6 meters per second square. Number one. After this, it moves with constant speed for next 10 seconds at 16 meters per second. It then decelerates at 4 meters per second square for the next 4 seconds and comes to rest. So this is how the overall path or the journey of the car will, or the motion of the car looks like. So moving ahead, it says part 2, it says calculate the distance traveled by the car during the 24 seconds of the motion. So the distance travel will be the area under the graph. So we're going to divide this. We have, let's call it 0, A, B, C, D, E. So I have a triangle OAC, then I have a rectangle ABCD, and then I have a triangle BDE. So if I'm going to calculate all the area, this will give me the overall distance traveled by the car. Okay, so distance traveled is equal to area under the graph, or let me divide it as area of triangle OAC plus area of rectangle ABCD plus area of triangle BCD or BDE, sorry, BDE. Okay. So first of all, area of triangle 1 by 2, base is 10, height is 16 plus area of rectangle 10 multiplied by 16 plus again triangle by 2, base is 4, height is 16. So if I'm going to calculate all of this together, it comes out to be 272 meters. Distance is 272 meters. Okay. Then it says calculate the average speed of car during its motion. So the average speed is equal to total distance divided by total time. Total distance is 272 divided by total time is 24 seconds. And this comes out to be 11.333 meters per second. So the average speed is 11.333 meters per second. Okay. Then a car, part 4, car journey travel at steady speed. It travels the same distance as fast. Draw the speed. So if a car is traveling at a steady speed and it wants to cover the same distance as this car, that steady speed will be it would be equal to the average speed we have calculated earlier. The average speed will be 10 so 8, 1, 2, 3, 4, 5. So somewhere here is what you get, 11.333 meters per second. So it will be a straight line that goes something like this till the end. So a car moving with a constant steady speed in the first 24 seconds will, and so this is the line we should draw draw speed time graph. So it's the speed time graph of the this case, or the second car will look something like the red line which I have drawn here. Okay. So moving ahead, part B of this question, or question 7, it says the thinking distance is the distance traveled by a car between the time that a hazard is seen and the time that the brakes are applied. The braking distance is the distance traveled while car slows down to rest. So in a table shown below, 7.1 shows the thinking and the braking distance of an alert driver when the car travels at different speeds. So first part, we have to complete the table. Okay. So the car is traveling at a speed of 20 kilometers per hour. Thinking distance is 9 meters and the braking distance is 2. Then it's double the speed. Thinking distance doubles. Uh, and the braking distance changes as well. Then at 60, we have to find out the value. And then again, the speed doubles. The thing again. So what we are seeing here, that as the speed doubles, the thinking distance doubles. So as the speed increases 3 times the initial speed, the thinking distance will increase 3 times. So it comes out to be 27. So you can always say 9, distance is 9, difference is 9, difference is 9. So that, yes, we are good. So this is the right value. So for this case, so it comes out to be 27 in this case. And it's always good, okay, to, check it thoroughly and give it a little time so that you have this this series of numbers correct, because if you're not going to have this correct, it will affect some of your values. So part 2, it says the time it takes for the driver to react to a hazard is constant at different speed. Explain how the table shows this. So let's try to find out time. So we're talking about, it's the reaction time. So the reaction time is the time that is basically thinking distance divided by this speed. So remember we are given the distance in meters and the speed is in kilometers per hour. So make sure the units are the same. So let's call the reaction time in seconds. So let me change the speed to meters per second. Is it a good way? Yes, meters per second. So 1 kilometer, remember, is equal to 1,000 meters, and 1 hour is equal to 3,600 seconds. So with this, the easiest to get is the reaction time. If I have to find out, let me use this as reaction time in seconds. So the reaction time in seconds will be 9 divided by 20 into 1,000 divided by 3,600. This will be my reaction time T. So this is 9 into 3,600 divided by 20,000, and it comes out to be 1.62 seconds. So this is 1.62 seconds. So let's find out for this. So 18 divided by 40, again, call it 18 multiplied by 3,600 divided by 40,000. Again, from here, it comes out to be 1.62 second. And you're going to calculate again using these two values, these two values, these two values. So all the reaction time will come out to be 1.62, 1.62, 1.62 seconds. So the reaction time comes out to be the same for all. So let's try to answer this. So explain how the table shows this. So we can say that, so the reaction time seconds is the same for all the um, values shown in the table table uh, um, which is 1.62 seconds. Okay, so this is so and so yes, I mean this is how also we can say that. So the reaction time and also write the reaction time is calculated uh, is the is you can say calculated as the ratio of thinking distance meters to the speed in meters per second. Okay, so explain how this is collected. So this is what we can easily say. So in part 3, it says what happens to the thinking distance and the braking distance when the driver is tired. So the braking distance, generally there is no change in braking distance, but what happens to the thinking distance is the thinking distance increases, or the reaction time increases. That increases the thinking distance. Okay, and this is uh, how you're going to answer this question. Okay, so moving ahead, question number 8. Question number 8, part A, it shows figure 8.1 shows us ripple tank and the crest of water wave that is produced in it. So this is a ripple tank. There is a wooden bar over here, and they're attached to a rubber band, and it is vibrating up and down, and it is generating some waves in the water, and crest and troughs are seen. So the frequency of water wave is 2 hertz, and the amplitude is 3 millimeter. Calculate the number of crests produced in uh, 1.5 seconds. So remember, frequency is equal to 1 by t, and this is equal to 2 hertz. So time period for one wave is 1 by 2 seconds, or zero point 0.5 seconds. Okay, so it means in point one, so in one in zero point 0.5 seconds, we have one crest. So in zero point 0.5 seconds, we are having one crest. So in 1 second, we will be having two crests. And in 1.5 seconds, we'll be having three crests. Okay, so total number of crests will be equal to 3. So this is one crest, and this is one trough. Moving ahead, part 2, it says the height of the wave is measured from the level of the undisturbed surface of the water, and the height of the wave at point O at time equals to is 0 at point time t equals to 0. So this here at time t equals to 0. On figure 8.2, draw a graph to show the height of the wave. So the remember the height of the wave is, or the amplitude of the wave is equal to 3 millimeter, and this is equal to the height of the wave, or the height of the wave is equal to the amplitude. Uh, so this is our undisturbed or reference case. So at so in one, and the frequency, remember, is 2 hertz. So in one cycle, there mean 2 waves are gone. So it would be something, 3 will be somewhere here. So let me try a dotted line here, and 3, it will go up and it will go down as well. So this is say 0.25, this is 0.5, 0.75, 1, 1.25, 1.5. So in first 0.25 second, it will go up and down like here, and it will reach its peak somewhere here and goes here. Okay, let me excuse my drawing. So make sure you have one complete crest and trough. So this is one cycle, and you have to just repeat it for the whole graph, and make sure you repeat it or you draw it completely. Okay, do not draw it or only one cycle, make it or draw it completely, something like this. So goes here, goes here, and it goes here and goes here. Okay, so the amplitude or height, this is the height. This is 3 millimeter up and 3 millimeter from the uh, baseline on distance. Make sure you draw it properly, and this is a symmetric wave. So always make sure that you draw it very neat and clean, and not like the one I have drawn, and I do not have the resources as you will have in your exam at the time of your exam. But anyways, always try to draw it as clearly as possible for the invigilators to secure complete grade. Okay, moving ahead, it says the frequency of the wave is increased. Describe how the apparatus shown in figure 8.1 is adjusted so the frequency of the wave can be increased. So remember, this is the equipment we have. So frequency of the wave, so you have this rubber band. So if you increase the number of rubber bands, it will, basically increase the amount of potential energy stored, and that will that will help you to vibrate the uh, wooden bar more frequently. Um, or you can use a heavier mass or a low mass wooden mass of less bar, that will also increase the frequency. Um, if you're going to move the wooden bar up and down more faster, it will increase the frequency. If you're going to increase the number of rubber bands, that will increase. As I've said, shorter and stiffer rubber bands will also increase the frequency. So what are the things? So easiest way is to say move the wooden bar up and down more frequently. This will increase in frequency, or use more number of rubber bands, or stiffer or shorter rubber bands will also do, or wooden bar of less mass or weight. So the best is to go with the first two. Rest, I mean, you can write any of these. It's a 1 point question, 1 point will give you this. So it says part 2, it says what happens to the speed and wavelength of the wave as frequency increases. Okay, so the frequency has increased. So remember, V is equal to F lambda. So frequency is increased, the wavelength will decrease, the speed remains constant. Okay, so the speed remains same, or wavelength decreases. Okay, so moving ahead, it says part C, shown below, figure 8.1 can be used to demonstrate refraction. So now we have to show refraction. So state additional operators to demonstrate this refraction. So if you're going to add a glass slab of certain thickness, um, inside the water, that will create two regions, one shallow region, or one deep region and one shallow region, and that will result and the refractions will appear, or a glass slab or a transparent slab, plastic slab. It's up to you. So add a glass slab or plastic slab or transparent plastic. Remember, this is important because you have to shine light and see uh, uh, to create a shallow and a deep region inside the water tank. Okay, so you can just simply have something like this. So moving ahead, it says draw on the level draw on figure 8.3 to show the refraction of water wave. Label a boundary wave where the refraction occurs. Okay, so now that is very important. So for example, so first of all, we have to, so I will use a couple of colors here. So first of all, let me define the boundary region. So let's say this blue line is my boundary region. That is, so for the boundary, so this is, say, my shallow region. This is my deep region. And this is the boundary region. Okay. Now I will be using the red lines, red markers to draw the waves. So now this is the wooden bar. This is going up and down. So the waves will be, remember, it's have a constant frequency. So equidistant lines, these will be my waves or wave fronts, and this is the direction of wave. So direction of wave. So this will be my direction of wave, and this will be going like this. So let me draw this, something like this. So you always, it's better to draw these lines with the help of a ruler, and that will make your life much easier. And this is the direction of the wave. So for example, consider the direction of wave something like this. This arrow shows the direction of wave. Okay, now I'll be using the green pen to draw the refracted wave. So remember, so deep, so your waves are bending, so going from denser region. So deep region is a denser medium, and shallow region is a rarer medium. So your rays are going from a deep region to a shallow region. So denser to rare. Uh, so what will happen to the speed? The speed will decrease. So deep to shallow, the speed will decrease, the wavelength will decrease, and the waves would be bending towards the normal end of the wave. Okay, so if this is the boundary, my normal will be something like this. So if I'm going to draw a normal to this blue line or this boundary, this normal will be something like this. Okay, so this is a 90-degree angle, the green line, and let me extend it like this. This green line is actually my uh, normal line. Okay, so again, always good to have a uh, ruler and a protector to uh, draw this line. So this is a 90-degree line. So denser to rarer, what will happen to the ray of light? So for example, this is red light, so denser to rare, incident angle towards the normal. It will bend something towards the normal, something like this. This is, will be, so this is my angle of, for example, incidence. This is my angle of theta r. This will be my angle of refraction. So now I have to draw the wavefronts with respect to this line. So I will be using black to draw it. So denser to rarer, it will be something like this. Something like this. Something like this. So what will happen over here? So this will be my lambda 2 and this will be my lambda 1. So lambda 1 will be greater than lambda 2. Okay. So lambda 2, you can say shorter wavelengths, larger wavelengths. See, so you can always draw a couple of shorter wavelengths compared to what your wavelengths are coming from here. So this is how you will be going to draw this diagram, and make sure you um, uh, draw all these things very precisely and very clearly to get complete credit. Okay. So now moving ahead, and the boundary label, this is, remember, the boundary where the refraction occurs. So this is the boundary where the refraction occurs. And the refracted, also the direction of wave of water waves will be something like this, in this direction. So the wave is coming in this direction and wave is going something like this in this direction of wave. And this is because of this glass boundary that is over here. Okay, so moving ahead, it says question number D, it says figure 8.4 shows a connection to the internet made from a remote station A using a satellite above Earth's surface. The data is sent between the stations A and B using microwaves which travel to and from the satellite. The station B is connected directly to the internet using optical fiber. The speed of microwave is given 310 power 8 meters per second. Station A and B are each 560 kilometers from the satellite. Okay, so remember this distance is 560 kilometers. This is 560 kilometers. Um, okay, and the speed of waves is c in 10 power 8 meters per second, the electromagnetic waves. So the first part, it says station A is 560 kilometers from your satellite. Calculate the time taken from data to travel from A to B using microwave. So from you can say A to satellite is equal to TA. This is distance 560 kilometers divided by 3 into 10 to power 8 meters per second. Remember, this is kilometers and meters per second. So this is time plus time from satellite to B. Let's call it TB. Again, this is 560 kilometers divided by 3 into 10 to power 8 meters per second. This is time 2. So multiply it by 1000. 1000 to make it meters, and multiply it by 1000 to make it meters. So eventually the total time is equal to TA plus TB, and this is 2 multiplied by 560 multiplied by 1000 divided by 3 into 10 to power 8, and this value comes out to be 0.003733 seconds, or you can say 3.733 meters. Oh, sorry, seconds. Oh, 733 milliseconds. Sorry, my bad. Okay, any of these values will help you. So it says that part 2 now, some data can be sent from A to B in shorter time along the surface of the Earth using infrared waves to carry the information in in optical fibers. State one property that infrared and microwaves have in common. So both infrared and microwave are electromagnetic waves. They both are, or just either use they or both, not both. So they are electromagnetic waves. Okay, this is we can call it electromagnetic waves, or also called transverse waves. Transverse waves. Okay. Then part 3, it says just one advantage of using optical fibers to connect stations from A to B. Number one, reduced cost. Again, satellite communication is very expensive, reduced cost. Other advantages, better bandwidth. You can send more data, better bandwidth. It's more reliable. You can say more reliable communication because there is a lot of information that is lost. And then there are security, or the more secure, you can say more secure communication, space communication. I mean, okay. So these are some of the advantages. If I would be a student, I would just simply go with either one or two. Okay. So next, so this is how you solve this question that was here. So then we are now the question. Now we are left with question number 9. That is the last question for this exam. So let's see. It says thorium 229 is a radioactive isotope used in several medical applications that involve alpha particles and beta particles. So part A, it says during ionization of helium atom, so during ionization, a helium atom becomes a helium ion. So figure 9.1 shows a diagram of a helium positive, H positive ion. So in part 1, it says state how the structure of helium atom differs from structure of the helium ion. So remember, helium atom and or a helium ion. So helium atom has 2 electrons, where ion has 1. So one helium atom has 2 electrons, while a helium positive ion has 1 electron. Okay, so the ion means positive ion means loss of electrons, uh, or you can say it helium atom has no charge, while He positive ion has a positive charge. So these are two structural uh, differences we can state. Okay. Then part two, it says state how the structure of an alpha particle differs from a structure of a helium ion. So alpha particle, remember alpha 42. This is so an alpha particle, remember, that do not have electrons. It has a charge of +2 and contains only positive, you can say neutrons and protons. So whereas a helium ion does have electrons in it. So simply an alpha particle don't do not have no, not particle doesn't doesn't have electrons. It has a charge of +2 and contains only uh, protons and neutrons. Okay, so that is how an alpha particle looks like or differs from a helium ion. So moving ahead, it says a nucleus of thorium-229 TH symbol of it decays alpha emission to a nucleus of an element X. Okay, then the nucleus of X then decays to a nucleus of Y by a beta emission. Complete the table below. 9.1 to show the number of protons and neutrons in the nucleus and in the nucleon, in the nucleus of X and in the nucleus of Y. So first of all, with X, 2 is gone here, so it comes out to be 88 here. And with 4 gone, so it comes 225. And X with the beta emission, so +1, so 225 will remain as such, so it becomes 89. It will be something like so number of protons for X. So this is the number of protons for X. Number of protons is equal. And the number of neutrons will be 225 minus 88. And this comes out to be 137. Okay. On Y, this is the number of protons, 89. And number of neutrons, 225 minus 89. It comes out to be 136. Okay. So this is how you just simply fill a table. Oh, pretty easy though. So moving ahead, in part B, it says experiments can show that a sample of material is radioactive. Okay. Describe the apparatus and the procedure used to show that a sample emits both alpha and beta particles. So we are concerned with beta and alpha particles. You may draw a diagram of the apparatus if you wish. Okay. So, well, there are ways to do this. So there is a one way is to go and use the material and the cloud chamber and see the patterns. But easier lab way, I would say, is to use a Geiger-Müller tube or a GM counter, sample and a piece of paper and a thin piece of aluminum sheet, and that will give you a good picture of what exactly we are having. So let's say we are having, let me draw, I will be using this. So this is my radioactive source. This is sample cover. This is source cover sheet. Then I have my GM counter. So this is say my GM counter, Geiger-Müller tube. And this is placed at a respectable distance. So I have a place a piece of paper here. Okay, so this is how I would use a paper or aluminum sheet. So an aluminum sheet, I will be using approximately 5 millimeter to, you can say, 8 or 10 millimeter thick. Okay, so these are a thin sheet of paper and almost 5 to 8 or 10 millimeter thick of aluminum sheet I need. So first of all, I will set up the apparatus like this, and so first of all, set up the apparatus as shown. Measure the background radiation. You can call it as lid. With no with no source or lid closed. So this is the radioactive source, and we close the lid, and so that there is no radiation leaking from this whole um, place where the source is kept, and we measure the background radiation. So we measure, and you can call it record. Recording is also important. Just measure and record the background radiation without the presence source using the GM counter. So this is our first step. Second step will be remove lid and measure the radiation at a distance d from the source. Again, measure and record. So I would just better to write measure and record. Record the radiation at source D. After that, to introduce paper sheet between the source and the GM tube, measure and record the reading. The reading will decrease as the paper blocks alpha particles. Okay. Then remove the paper and introduce the aluminum sheet. Measure and record the readings, the GM counter will show negligible or background values. Okay, because aluminum sheet blocks both alpha and beta emissions. Okay, so this is how you will be able to see or use an experiment or devise an experiment to see whether a source emits alpha and beta emissions. So in this case, remember, if your GM counter will be showing some reading after introduction of the aluminum sheet, then it means that your source is also emitting some gamma radiations, and that is, I mean, it's dangerous for you as well. So, but anyways, this is how you will write it, and I would just recommend you to uh, summarize it in your own words. Make sure you draw a good diagram, not like me. And voila. So moving ahead, question now, last part of our question number 9, or the last part for this exam. It first says, state what is meant by half-life of thorium. So the half, it means that, or we can say that it is the time it takes for the thorium 229 isotope to decay to half of its value. Okay, so this is the time, or half of its value, or you can say also write it half of its or radioactive levels, or half of its original mass. Original mass. Okay, so something like this will or half of its original value, not mass, or for its original value mass, so something like that. So this is how or what exactly is half-life of an isotope is. It's time to decay to half of its original value, or half of its original radioactive levels. Okay, so in part 2, it says a sample of pure thorium 229 contains 4 into 10 to power 14 atoms. And after 22,000 years, the number of atoms of thorium 229 in the sample is 5 into 10 to power 13. So it says determine the half-life of thorium 229, and we have to show our work. So remember the formula. So time it taken, an initial value, half of time of it by t divided by the half-life. So NT is the you can say the final value after time t. Uh, that is the value, and time t, or you can say that at time t is the time, so you can initially say that the initial time, or the time period is, or the time span is 22,000 years. Time t by 2 half we have to find out, uh, and not initial value. Initial value was 4 into 10 to power 14, and the value after time t, or 22,000 years, or after a certain amount of time, or whatever the time that was that has passed is 10 to 10 5 into 10 to power 13. Okay, so after time t, 5 into 10 to power 13 is equal to 4 into 10 to power 14 multiplied by half raised to power time, or time is 22,000 years. 22,000 years and divided by t half. So half-life here. So what comes out to be 5 into 10 to power 13 divided by 4 into 10 to power 14 multiplied by 1 by 2 to the power 22,000 divided by t half. So taking log on both sides, what we are left with is t1 by 2 to come up equal to 73331 by 3 years, or equals to 733.333 years. Okay, so this is how we solve it, or let me remove it from here and show you a little bit more of how we came up with this value. So what we are left with is say 5 into 10 to power 13 divided by 4 into 10 to power 14, this value. And if we take log on both sides, a natural log, so it will come out to be 22,000 divided by t half natural log of 1 by 2. Now it becomes more easier. So t1 by 2 is 22,000 times natural log of 1 by 2 divided by natural log of 5 into 10 to power 13 divided by 4 into 10 to power 14. Okay, so if you solve this, this comes out to be 7333 power 1 by 3 whole power 1 by 3. So the half-life would be equal to 7333.333 years. Okay, so this is how you solve this question, and this is how you solve, or you get your value of half-life. So thank you very much for listening, and I hope you have learned something from this effort, and I wish you all the best for your exams and future years to come. Thank you very much. Take care. Bye-bye.